Hello, it's a crazy math nerd back at you. In the last video that I made a video called Volume of Known Cross Sections Coming from a Given Base. And basically what that was is you knew what the base, like for example, this was the base of the last one that I talked about. This is the base, this outline right here. This was the base. And coming out of that base were squares. And if you did that, it would make a very strange solid. And in order to find the volume of that solid, we discussed that we're going to add up, integrate from 0 to 4. 0 to 4, that's 4. We're going to add up all the areas of all those squares. And if we do, we get the volume of that solid where the squares are coming out of that base. So that's what we talked about last time. We're going to play on that idea, except in this time, in this situation, we're going to talk about volumes of solids where we revolve an area around an axis. So this is very visual, and I don't draw this well, so I'm going to ask for some help from a computer program called Calculus of Motion. So here's what's going to happen. You will be given an area. So this area is this pink area from A to B, and it's under the function root x. And you will be asked to rotate it around a line. The line will either be, and the line will be parallel to either the x-axis or the y-axis. In this case, it's parallel to the x-axis. See this axis of revolution? So what we're going to do is we're going to show you what happens when you reflect the area across that axis of revolution. So that's just reflected across. And then we're going to ask you to think about rotating that all the way around. What would happen if you rotated that rectangle all the way around? Then you would end up with a circle, see that makes a circle, with a hole in the middle. It's also a circle. So it's like a big circle, and then they have a hole, and that reminds me of a donut, because I love donuts. I live right down the street from a Krispy Kreme. It's one of my favorite places. I don't go often, but I do love it. So what would happen if I wanted to find out how much area this donut has? Okay? If I wanted to do that, I would have to take the area of the outside circle and subtract the area of the inside circle to find the donut. Well, that's one of these donuts, and I'm going to make it really thin, and then I'm going to add up all of them. So what I'm going to do, hold on a minute, let me take a picture of this so I can write on it. Is I am going to, move it a little bit, I am going to add up from A to B. Notice when I said add up, I did the integral, because that's what integration does. It adds up whatever follows it. The area of the donut, of the circles. And why did I say circles? Because there's an outer circle and an inner circle. So let's write that. I don't like that. Let me go erase that. Let's say this. We're going to add up the area of the inside circle. And you know that inside, oh, Lord have mercy. Sorry about that, y'all. The area of the outside of the circle. Minus the area of the inside circle. And what that's kind of like, it's kind of like making the whole donut and then the entire donut and then taking the hole out. Have you ever had donut holes? They're great, by the way. And we're going to do this with respect to x because we're going around an x-like axis, okay? So the area of the outside circle minus the area of the inside circle, see that little pink part right there? That's what that would be. And I want to add up all of that. So all of that on the integral. Adding up from A to B, the area of the outside circle minus the area of the inside circle gives me all that pink. And if you stacked all those on top of each other, you would get a solid, and this would give you the volume of that solid. So let's do this. Let's give some letters to this. Because the area of the outside circle, we're going to call this pi big R squared. And so that means that the distance from here, I can do this straight, and I cannot, so we're going to cheat and use my line feature. The distance from, here we go. The distance from here to here is going to be called big R. That's big R. That's from the axis of rotation to the most outside circle. That's the radius of the big circle. The little circle is right here. Again, I need to cheat. Now that's terrible. I can't draw a straight line with this thing, isn't it? Let me see if I can find that color. So this little guy, because he's a small radius, we're going to call him little r. Okay? So the area of the outside circle is pi big R squared, and the area of the inside circle is pi little r squared. And if we add up all of those, we will find the volume of this crazy solid that, oh, I don't know what that is. That's a crazy tower thing with a cylinder in the middle, isn't it? So if I wanted to make this a little simpler, I might. So to make this a little simpler, we're going to factor out the r here, the pi. So it's pi, adding up all those areas of the circles, we'll just take the pi out, of r squared minus little r squared. Area of the outside circle minus area of the inside circle. Okay, I didn't write the word circle up here, did I? I'm just a little crazy. Circle. There we go, inside circle. All right, so here's what we got to do. Now we've got to figure out what is that distance from the axis of revolution all the way up to the function. Because see, doesn't this change every time? See, look how there's, that's really hard to see, isn't it? Let me go back to the little screen. See how they change? See how the outside changes? The inside doesn't because it's solid, but the outside changes. So it's going to be it's going to relate to that function. So here we go. How do we find the distance of that? This distance, according to this is a 2, negative 2. So that's the distance of 2. So that's 2, and this is the distance of the function, which is root x. So big R, A to B, big R in this case is 2 plus root x. And we're going to square that because that's what our formula is to find the area of the circle, pi r squared. The distance from here to here, we've already said is 2. We did that analysis when we tried to find that. So that distance is just 2. Okay? So minus 2 squared. And if we knew what A and B was, and we could figure that out, but if we knew what that was, we could actually plug that into our calculator and find it, or we could actually square it out and do it by hand. But the big thing I want us to get through this video today is to talk about conceptually what are we doing when we find volume of solids by revolution. We're taking an area, revolving it around an axis, we're slicing it into circles, and we're slicing it into circles, and we're adding up the area of the outside minus the area of the inside, and then when we do that, we get the volume of the solid. Okay? I'd like for us to look at this problem, and we're just going to look at it conceptually, and then in the next video, we're actually going to work it and get the calculator out and do all that. But I just want you to conceptually understand this. All right? It says, let f be the function given by da. So this little guy right here is that. That is that function, that polynomial. And this tangent line has nothing to do with r, because we're going to be looking at finding C. And C says find the volume of the solid generated when r is revolved around the x-axis. So notice that r contains all of this. That's all of r. So I'm trying to revolve this around the axis, sorry. And so what I'm going to do is when you revolve it around the x-axis, it is going to be, because it is what we call flush to the axis that's going around. When you revolve it, then there won't be that hole there that we had in the last thing. So when you revolve this guy around this axis, it will, for example, if I did this, that means that it would go around like that. See what I mean? And oopsie, and it would be flush to the axis. So that is kind of different because we don't have that inside radius. There won't be a hole in it because see how that line from the axis up to the function is hitting all of that area, so there is no hole. So in this one, we would be going, we're going to add up all of these. Here we go. Here they are. They're coming out. Here's all those things that we're going to revolve around and make circles. Not hard to see. Like that. I can't go wrong. All right. So when we do this one will be a little easier. So we're going to go from 0 to whatever this value is right here. And if I factor that out, if I factor this guy to find that root, if I take an x squared out, and then that leaves me 4, right, minus x, then x equals 0 will be a double root, and x equals 4 will be my other root, so that value is 4. Then we go from 0 to 4 of the outside radius. We're going to take that pi out. Let's leave it in for just this problem. So pi r squared, the radius is going to be the function's height. So pi r squared minus pi, and the radius on the other one is 0 because there is no donut hole to take out of this. This will be a solid slice, and this will be called a disc. If it is solid, what you're rotating is flush up against the axis you're rotating, it's called a disc, like a frisbee. And if your area, see this was rotating around something way down here and there was a hole in it, this is called a washer because it looks like a washer, which is used when you're putting things together and you have a, you're trying to screw a nut into something and you don't want it to go into the material. You put it between the nut and the material and it keeps it from going into the wood or going into the metal or whatever. And that's a washer. It's a little thin metal thing. So if the area that you're rotating, and you know what, let's go back and look at that. Let me show you that. So this guy had a hole in it, right? So let's do this. I'm going to reset this. Let's change the axis of revolution all the way up to the x-axis. And so now when we rotate, see your reflected area is right there, and now when we rotate, notice there is no hole. So it is, you don't have to do that subtraction of the other area of the inside circle because there's not an inside circle. So this particular picture, which we're going to take a picture of, is a disc. This is called a disc. When your area that you're rotating around is flush to the axis of revolution, it is a disc. When your area is not, your area was not flush to this axis of rotation, there's a hole in the middle, and that's called a washer, and you have to subtract the inside circle. So back to the problem at hand. In this AP problem, we did pi r squared minus, and really you don't have to do this. That's just kind of, silly. But I was trying to tell you, if you'll think about outside circle minus inside circle, you'll never miss it. Because if there is no inside circle, you just have that as 0. Okay? So this is an introduction to the volume of solids by using revolutions. So you will either have a disc if the area that you're rotating is flush to the axis, or a washer if the area is not flush to the axis of rotation. And all you're doing is you're doing area of the outside circle minus area of the inside circle on a given x interval. Okay? So hope this has helped, and in the next edition we'll actually work that problem that we were doing just a minute ago.